Hello, this is Fayaz, and today we are going to be talking about the cat and mouse puzzle. So a while back, I watched this video on this excellent channel called Numberphile. Great work, Numberphile guys. You're awesome. The link to this video is in the description, and do check their channel out and subscribe to it as well. The cat and mouse puzzle, the Numberphile guys solved this puzzle using a mathematical strategy, and that inspired me to see if we can solve the same puzzle using a neural network, and that's what we're going to be talking about in this video. So before moving on to the neural solution, of course, I need to give you a brief overview of what the puzzle is all about. So imagine once upon a time there was a cat and it was chasing a mouse. Okay, childhood memories. That since the mouse isn't looking where it's going while being chased by the cat, the mouse falls into a pond. So that's the mousey in the pond. You see that? Now the mouse can swim, so it can swim in these 8 different directions at any given point in the pond. And it can swim for a while. It cannot swim indefinitely. So the mouse can swim for, let's say, t time steps. And the cat, on the other hand, is scared of the water and doesn't like it much. So it won't be jumping into the pond to chase the mouse. What the cat does is that it tries to circle around the pond at the edge of the pond to see where the mouse would exit. So it tries to anticipate where the nearest exit point of the mouse would be, and then it tries to move on the edge of the pond towards that point all the time while the mouse is inside the pond. And the cat also has a certain advantage. It is about 3 times faster, or let's say m times faster, on the edge of the pond than the mouse is in the water itself. Now, this puzzle, there is no puzzle up till now. The real question here is, starting at any given location, can the mouse obtain a sequence of these directions to swim in so that it escapes from the cat while the cat is giving it chase from the edge? And that is what the puzzle is. Now, this is a slightly discretized version of what the Numberphile guys did, but this is the one version that I'll be using in this video. Okay, so let's move on to, and if you don't like this cat and mouse story, you can think of it as an alternative scenario. Imagine if you're celebrating Eid and you get a goat for yourself that you want to slaughter and barbecue. But the goat is smart and it sees its impending doom. So what it does is that it runs away, and then it runs and falls into a pond while you're chasing it. Since you're wearing your new Eid clothes and are all dressed up, you don't want to enter the pond and get all wet. So it's the same story over and over again. And what you see on the screen is actually a real runaway goat that gave the police and other authorities a hard time in New York, I guess, while being chased by them. Okay, and it was really smug at the end. But you get the idea, right? You can either assume a goat or a cat or a mouse, whatever you want. Okay, so that's the theme of this problem. Now, the solution that we want to do is whether to see if we can make a mouse brain, a small mouse brain that allows us to solve this puzzle. What that means is that we're making a neural network that observes where it is, where the cat is in the environment. So that is observation. And then it sends this as a state vector to the brain, to the mouse brain, which outputs an action of what direction to swim in at the current location. And then that action is executed by the body, and the position of the cat and the mouse are updated in the environment. If the mouse escapes or if it's close to that, then it gets a reward. And if it sadly dies away, it doesn't get that reward. So we want to essentially use that reward signal that the environment is giving us, or the mouse, to help the mouse develop a strategy or a policy that allows it to escape. So the objective is, what does a solution mean here? The solution means that if we know where the mouse is, or the current state of this whole system, that is S, then we want to find a function called pi that maps these states to actions based on rewards from the environment. So an optimal policy would be, we denote it by pi star of S, that gives the mouse what action to execute at each given state, so that the mouse can escape from the cat at the end. Okay. So that is what we really want to do in this video. And for that, we'll be using traditional neural network reinforcement learning strategy called Qlearning. And this is a really interesting way of learning from the environment, learning from rewards using neural networks. And the idea is pretty simple. So some states in a given system are more desirable than others. So for example, if you see this cat and mouse game, then if the mouse escapes from the pond while the cat is far away, then this is a really desirable state for the mouse at least. Okay. On the other hand, if the cat is hugging the mouse, uh, that is not so much desirable for the mouse. Okay. So what happens then if not only that is that there are some states that are actually better than some other states. However, in a given state, so imagine a state just before either one of these states, and so you have the mouse over here and the cat over here. Imagine this state of the system. Some actions in this state lead to better states than other actions. So for example, if you follow this red arrow, then the cat might hug the mouse, which is not a good outcome. However, if it follows the green arrow, then it might swim away from the cat, leading to a higher reward in the next state. So that is essentially the idea. We want to take actions that maximize our future rewards or whenever we receive a reward. Yeah? So we implement this idea using what is called a Q function. So a Q function is a function of two variables. One of them is a state and the other is action. And it essentially tells us what is the quality or expected payoff of executing action A in a given state S. So it tells us the usefulness of an action in a given state. Once we learn this Q function, QSA, then what we can do is we can find the utility of any given state or how useful that state is by seeing which action gives the best Q value across all possible actions in that state. So that is the utility of any given state S. And we can also find the policy. So the policy, once we know QSA, then the policy is a simple matter of identifying what action to execute or what's the best action to execute in any given state. So that's a very simple implementation. So finding QSA is key. Now the question is, of course, how do we learn this function, this QSA? So how do we find which actions are useful in what states? Of course, we can ask an oracle. So that would be supervised learning. However, if that is not an option, then what we can do is learn from the rewards that the environment is giving us. So what we do essentially is that we start off taking random actions in the environment, and as we execute those actions, we get some reward from the environment, and then we use that information to build our Q function or learn our Q function. If the new state that we move from by executing a particular action in a current state is desirable, then the Q value of that action in the previous state should be increased because it has led to a better state. And that is a simple idea implemented using what are called these Q update equations. So we start off with a random Q function, and then we constantly iterate on it to improve it based on the rewards that we see. So the new value of the QSA in a particular state S and the action A at time t would be based on how much reward we received by executing action A in state S and what was the utility of the next state. So if the next state is really useful, then the reward of then the Q value of this action in the current state is increased. And if the value of the reward that we have received in this state by executing that action, if that is high, then the Q function will also be high. And this parameter gamma that you see over here controls the trade-off between the reward, the current reward, and the future payoff. So this controls the greediness of your agent. And of course, if the value of your Q function in the current state is already high, then we can control how much to increase or decrease it based on this alpha parameter. And we've already have the definition of the utility, which is simply the maximum Q value of any action in a given state. So we simply substitute that, and then this becomes our update equation. So just to recap, what's going on? If you lost your mind, don't worry. This is really easy. So if you have, imagine if we are trying to build this Q function for the mouse, and we start off with a completely random Q function. So initially it would be executing random actions in different states, but it would be getting rewards, either penalties or rewards, based on its action. If a particular action in a given state gives it a higher reward, the Q value of that action in that state would be increased. And if this action leads to a state for which the Q value is high, then the Q value of this action in that previous state is also increased. And that is essentially the idea. And what we want to do is to implement this using neural network. So this Q function would be implemented as a neural network. So we know that neural networks are universal functional approximators. So any function out there in the universe can be implemented using a neural network. We can implement the Q function as a table, but if the data is not discrete, then the table would be really, really large, or it might be infinite in size, or if the action space is not finite, then this would be a very large table or an infinite one. However, a neural network will always be able to approximate or implement this Q function because it can take in these continuous variables and actions. Okay. So in order to implement this, there are three major things that we need to implement. The first is a simulation environment. So we do that by making some assumptions. So we assume that the pond is circular, and we have it center denoted over here in the black dot, and its radius is equal to 1 unit. We model the position of the mouse at any given time by as a single dot, and we use polar coordinates. So that if the mouse is at a distance p from the center, we denote it as p theta. That is the location of the mouse, and the mouse can move at any given time step in one of these 8 directions by an amount d. So d can be, let's say, 0.05 if it can. So in a single step, the mouse can move a distance of 0.05 units. The cat, since it's always on the edge of the circle, therefore we'd only need its radial coordinate to determine its position. So we only use this phi angle to model the position of the cat. Okay. Now the cat, as we talked about earlier in the puzzle, can move a distance m times d. So if the mouse can move a distance of d, then the cat can move a distance of m times d along an arc at the edge of the circle. Okay. Now, the cat always moves towards the nearest exit point of the mouse. So if the mouse is over here, its nearest exit point is where the location of the mouse can be extended towards the edge of the circle. So this is the nearest exit point. So if the cat is over here, then it will always try to move towards this exit point. It won't go over that way. It would try to come over here because that is the shortest distance between this point and the mouse's expected or anticipated nearest exit point. However, remember that the cat can only move a distance m times d. Now, the mouse knows where the cat is, and we model that fact by modeling this vector that is shown in purple over here. So it's the vector starting at the mouse and going to the cat. So we model that vector. So in order to determine the state of this system, there are only 4 things we need to know. Actually, it's lesser than that, but it's okay. We need to know where the position of the mouse is, and we do that. We determine the radial position of the mouse at any given time, t by pt. We know where the cat is, or where the cat is relative to the mouse by using this vector delta x delta y, and we also monitor the health of the mouse. So that is the state. So as the time increases from 0 to t, the health of the mouse decreases from 1 to 0, at which point the mouse sadly passes away. Okay, so that's the basic implementation. Now, if the mouse executes these sequence of actions and then it crosses the edge of the pond, that is, comes outside the pond, and its current position at the exit point is not what I call bounceable, that is, not reachable by the cat in the current time step, then the mouse has escaped. Otherwise, the cat hugs the mouse at the edge. Okay, so that's not a good outcome. And we implement the second thing that we really need to implement is a reward function. So the mouse is rewarded based on whether it is able to survive or not, how far away it is as it escapes from the cat, and how much health does it have as it escapes. So the complete implementation details of this reward function are given in the code that I'll be talking about in just a bit. So in order to implement this whole scenario in the form of in the context of neural Qlearning, we implement a neural network. What we do is that we use a very simple neural network that takes in, so we want to implement this function qs comma a. So what we do is use a very simple neural network that takes in the state vector and then produces q values for each action, each of the 8 actions that the mouse can take in that state at the output. So that's how we implement this Q function. We denote it by a neural network QNNSA with learnable parameters W. So the neural network we use is a very simple neural network. We use a single hidden layer. So there are 4 input neurons because there are 4 elements in our input vector. There are 8 output neurons because we need to implement the Q function that has 8 outputs corresponding to the 8 actions that we can take. And then what we have in the middle is a hidden layer in which we have 76 different neurons. Now what happens, or the way it works, is that initially we execute what is called an episode. So the mouse starts at a random location within the pond, the cat starts at a random location outside the pond, and then at each time step, depending upon what action we get from the Q function from our policy, we update the position of the mouse and accordingly the position of the cat itself. And we keep on doing this until either we run out of t is equal to, let's say, 500 time steps, or the cat catches the mouse, or the mouse drowns. And at which time we end this episode. So we do this for multiple episodes. However, in each episode, the Q function is being updated. And it's being updated based on the reward that we get, based on the utility of the next state in which a particular action leads us. So imagine if the current value of the Q function in state S is QSA, then the execution of this action changes the state, and at that point, what we do is that we get the target value or the next Q value that we want to update. And that target value is used as a neural network target, and then we try to make the neural network learn this new Q value and update it from its current point. So that is how this whole episode works. And if you do it for a sufficient number of episodes, you can probably execute this whole code. So the thing is, this code is available for you to use at this given link, and you are welcome to try it out. And I've also put a saved model that gives the best accuracy. The model that I used was trained for about 200 episodes, and depending on random locations. And the cat was taken to be 3.5 times faster than the mouse, okay, during training. Okay, and these are some of the results. So some visual results finally, right? So you can see the mouse over here moving around within the pond. Let's take another look at it. But it started at the origin. This is the mouse. The cat is denoted by the black triangle, and the mouse starts at the origin, and then it moves around trying to escape from the cat until it finds the way that the cat is far away, and then it just exits. So this is pretty good result. This is another simulation. This is another episode. The position of the cat is different, and you can see that the mouse moves around until it escapes. The cat almost got it, but ultimately the mouse escaped. So that's another success. Let's take another look at some more videos. This is the mouse is moving around the pond, and as you can in the pond, and the cat is moving around at the edge of the pond, and the mouse ultimately escapes. This is another video with the same. You can see the mouse escapes pretty neatly this time. So it starts over here and then it just follows an arc while the cat has to take this longer route because the mouse's anticipated nearest exit changes like that. So the mouse fooled the cat real well. Okay. So I also have some quantitative results. And what's interesting is that if you train this whole neural network strategy with a multiplier factor of 3.5, we get a success rate of 84%. That means if I run this 500 times, let's say, 100 times, let's say, then 84% of the time, starting at any location, the of the cat, the mouse is able to escape from the origin. So you imagine the mouse at the center of the circle and the cat at any location at the edge of the circle. And we allow this, we use the trained neural network, the policy of the trained neural network, and we get a success rate of 84%. Okay, we start the mouse at the center because that is essentially the most difficult spot where the mouse can start, and it's the most generalized one as well. The great thing about this implementation is that even if you increase the multiplication factor during testing, while the neural network has been trained with a multiplication factor of 3.5, it still doesn't fail until the multiplication factor goes up to 4.7. So at a multiplication factor of 3.6, we get a 62% success rate, which is pretty good. Remember, even if we know one strategy that takes the mouse out from the center of the circle, then we can essentially generalize that strategy for any given location, starting location of the cat. So we just need one success at a given multiplication factor, and then we can use that strategy and just rotate it. Okay, so it's rotation equivariant sort of. Okay, and then we have if we increase the multiplication factor to a factor of 3.7, we get a success rate of 54%. The best thing happens if you keep on increasing the multiplication factor until, let's say, 4.6, and there we also get some successes. Okay, and then if you increase the multiplication factor to 4.0, 4.7, that is where we don't see any successes for this particular model. Okay, this is the mouse escape strategy for when m is equal to 4.0, and this is a really interesting one. And remember, the neural network has not been trained on this multiplication factor. Okay. Okay, the mouse starts at the origin, and then it just keeps on going in circles, and the cat goes around circles along the edge of the pond. The mouse ideally wants the cat on the other side of the pond when it attempts an escape, and that is the sort of strategy that the number file guys got. And it's not exactly the same strategy, but the mouse is able to escape, and escape by some margin here as well. So that's a really good success of this strategy. So I'm pretty happy about this result, and I hope you have enjoyed this video. And please take a look at the code and try to model it and improve it even further. You can get rid of the discretization that I've used. You can use continuous sections or whatever you like in that. And at the end, I would like to thank you for your patient listening.